today here we will be discussing about Kubernetes native DevOps system for AI and ML workloads. So in next 45 minutes, we will be going through various challenges. We will discuss various challenges which we face when we try to run AI and ML workloads in Kubernetes. And there are various frameworks to mitigate these challenges. And one of those frameworks are Volcano. And we'll see how Volcano addresses these challenges. And I have a demo video which shows like complete, like how we can run these AI and ML workloads in any of the clouds which has a Kubernetes cluster. Okay, so this talk is not about whether we should use Kubernetes or not, or whether Kubernetes is the best way to go around the DevOps system. But this talk will focus on whether if you are running your workloads on Kubernetes and some of your workloads are AI and ML workloads, then what is the best way to run those workloads? And what is the best and efficient way to run those things? So this talk is all about that. So to start with, the challenges what we face when we try to run any of these HPC workloads in Kubernetes is batch provisioning. So all of these workloads run in batches. These are short running workloads. These are not service workloads. So they start in a batch and they finish their work and then they go. So if say if it is a TensorFlow job, right, and you have a set of PS and a set of worker which needs to come up in a batch and then it can start the execution. So these all things needs to come up in a batch. So by default, any of these schedulers are trying to run or schedule these workloads one by one. So it is like wastage of resources, and plus it won't be able to start the execution unless and until the complete set comes up. So second thing is like job management. We need a better understanding of how these jobs run so that we can suspend, resume, or start these workloads. Third is data management. All of these type of workloads basically deals with various levels of data. The data is transferred between the different tasks. So we need a better way to understand how these data are flowing. And we need a data management layer which can actually manage all of these data. And then all of these type of workloads actually have multiple templates. Say again, example of TensorFlow, we have a PS and we have a worker. These two PS and workers can have a different template, can have a different Docker image itself, can have a different CPU requirements, memory requirements. So this complete set can have a different templates for different type of tasks, and all of these needs to run together. And then we should have a different error handling scenarios where like you have to define that if any of these tasks fails, what needs to be done with the job. Okay, so if any of these, say a worker dies, a worker pod is evicted, or that task is killed, whether the whole job needs to restart or just a worker can restart and the work can go on. Then some of these ML, AI and ML workloads like MPI and all, they need indexing of the jobs because based on those indexing, they try to communicate with each other. And all of these batch workloads comes either depends on each other or they have a particular execution flow. So we need to understand what is the dependency between all of these tasks, and based on those dependencies, we need to provision this workload. And some of these tasks also needs a delay in the pod creation, like if a master and worker is there, so master needs to come first and then the worker needs to start. So these type of scenarios are also there when you are trying to run any of these HPC workloads. So if we try to evaluate all of these challenges in Kubernetes, we have a service workloads which are already well in place. Okay, you have a lot of options to run these service workloads in Kubernetes. But if you go to any of these high performance workload like TensorFlow, Apache Flink, or Spark, and then there are a lot of gaps, and you cannot run any of these workloads in a vanilla Kubernetes. You need a certain type of frameworks to understand these framework and then deploy it. So to evaluate the Kubernetes gaps, like we have in the job segment, in the queue and a job segment, we have like we don't have a multiple pod templates. Okay, we don't have a proper error handling scenarios, and we also don't have a delay in a pod creation, or we don't have an hierarchical queue. Okay, for runtime, we don't have multiple runtimes available. For schedulers, we don't have fair share scheduling or queues or preemption reclaim or batch scheduling. Okay, so based on all of these gaps, we have a framework called Volcano. This is an open source project which was open sourced like 4 to 5 months back. Okay, right now it is in right now it is planned to move to CNCF sandbox by end of this year. Okay, and this basically the overall architecture for this Volcano framework is like we have a set of CRDs, controllers, and schedulers. CRDs are basically the custom resource definitions, and controllers are the one which does the data management and the job management, and the scheduler is the one which tries to schedule all of these jobs properly. So we have logically divided Volcano into two different segments. One is the domain framework, where we try to understand the domain and we try to map the domain objects to the Kubernetes object. Okay, and then we need to enable the certain features, like certain features for domains, right? We need to understand those features, and we need a way to enable those features in the Kubernetes layer. And then we have a common services, which are basically schedulers and a command line tool to manage all of these jobs. So coming to the architecture, all these green boxes are basically the part of Volcano. So we have a controller, we have a schedulers, and if you try to run any of the jobs in Volcano, like you just need a kubectl command line tool to run those jobs. So once you try to run those jobs, our controllers pick up those jobs and try to see what type of scheduling it needs. Based on the scheduling nature, it tries to schedule the jobs in the Kubernetes. And the main part of this, the core component of Volcano is the scheduler. That is where our USP is basically. It tries to schedule in the batch and tries to deal with lot of scheduling algorithms basically. So all these algorithms are basically plugged into the scheduler, and if you want to write your own scheduling algorithm, you can write and plug those algorithms inside the scheduler itself. So coming to the scheduler, it does the gang scheduling. So the way it does is like, say you have a green set of workloads and you have a blue set of workloads, and there is a condition that all of the green workloads or all of the blue workloads should be scheduled in a batch to finish up the work. Okay. So in most of the cases, Kubernetes has a default scheduler which tries to pick up these jobs one by one and tries to schedule it. So if you go by a default scheduler, it will try to pick up randomly the jobs, like from the green it will pick some, and from the blue it will pick some, and it will try to schedule. The jobs are scheduled, but there is a condition like all the blue jobs should be scheduled to start the execution of the job, right? So in these cases, the deadlock comes because even the blue jobs are not able to schedule because 2 of the pods are still not running, and even the green jobs are not able to schedule because 3 of the pods are still not scheduled. So this results in the deadlock. Another is like busy waiting. Like say, if all the blue pods are scheduled, okay, and 2 of the green pods have been scheduled, but it cannot be run because it needs a complete set to come up. So it's like 2 of the resources have been consumed, but it is it cannot be used in any other sense. So here is what we do is, we group all of these pods in something what we call as a pod group, and we specify that, okay, at least this number of pods or this number of tasks should come up before we can start the execution. So we pick this set and we try to schedule these sets one by one. So if the green pods have to be scheduled, right, we try to find the minimum number of pods which should come up to start the execution. Based on that, we will see the current criteria, current resources, and if the current resources can schedule the complete job, then we reserve all the spaces for us, all the resources, and then we start scheduling one by one. So this way we make sure that the complete set is running in one time. So when we implemented this and we tried running it against the default scheduler of Kubernetes, first we ran like one job with 2 PS and 4 workers. Okay, when we tried to run it with Volcano is this one. Okay, and the red ones is the default scheduler. When we try to run this it was able to complete the whole job in 24 minutes. Don't go about the time. It is like this time is taken by the jobs to complete it work. The scheduling might be just 1 second or probably less than that. Okay. When we increase the number of jobs from 2 jobs to the 2 job, where is like 4 PS and 8 workers, the default scheduler, because the case like this one, it went into the busy waiting. Okay, because already one of the job is running, okay, and another is still like the whole set is not running. So the default scheduler took like 36 minutes to complete the work, complete the whole job, whereas the Volcano was still able to complete the whole job in just 24 minutes by intelligently scheduling it to the proper places. When we increase the job count to 5, okay, the Volcano was still able to do the complete, was still able to run the complete job in just 24 minutes, but the default scheduler took more than like 36 minutes. Actually, most of them went into the deadlock scenario, okay, and 2 of the jobs was not able to complete itself because they were all busy waiting or either in the deadlock scenarios. So this test results are already out there. You can just click a link and go to this test result. So this way we were able to like scale up the resources and still have a better scheduling algorithm to run these jobs. And then just gang scheduling or batch scheduling was not enough. So we tried with the backfill, where whenever we have an empty space or empty resources, we try to search for the jobs which needs a very low resource. Okay, just like the brown ones. Okay, it needs just 2 pods to complete the whole task. So we try to pick those small resources, a small task, and we try to fill it wherever it is possible. So this way we were able to utilize the whole resource what we have. And third is like fair share. So backfill was also not enough. So we went with the fair share, where we say the green job belongs to one tenant and the blue job belongs to another tenant. And both the tenants are sharing the same resource. So here the tenants can be like namespaces as well. Okay, so since the blue job has the more count, okay, by default a scheduler will try to pick up those jobs and try to schedule it. Okay, so but the problem here is like the green jobs will always wait for the resources to be empty and then it can be scheduled. So what we did is like we started giving a particular weight to all of these different tenants, and based on the weightage of the tenants, the resources will be allocated to them. So this is like fair share. So even that was not enough, so we went to another thing called reservation. So if we keep backfilling all those resources, small task in the empty spaces, probably the task which needs the whole set of resources will never get scheduled. So we do backfill on the alternate basis, as well as there is a priority by which we can define like, okay, the task which needs the whole resource, okay, we can assign the weightage, and based on those weightage, we can allocate those resources. So this is how we did reservation and all. So if we consider a simple scenario of an MPI, if you want to run an MPI job and say it has an MPI run and a different 3 workers, the scenario is like you have, first of all, you have an MPI run and the workers. These both tasks have a different template. They have a different Docker image, worker has a different Docker image. These might need a different CPU and memory requirement. Workers might need a different CPU and memory requirement. So we try to make a template where you can fit the multiple, we try to make a Kubernetes object where you can fill those jobs with a multiple pod template. And you can define the life cycle of these pods. So you can say if the worker 3 dies, you need to restart the whole job, or you can just respawn the worker 3 and start the execution. So these type of scenarios are already there. And you can also define like if all the like worker 1, worker 2, and worker 3 finishes up the job, you can say that, okay, the complete job is finished. So this type of lifecycle policy management you can do, and you can enable the gang scheduling in these things. And basically, these worker 1, worker 2, and worker 3 needs to connect to each other seamlessly. So what we did is we started creating the headless service for each of these tasks. So we create these services and we try to mount these service informations in one of the locations called etc volcano, /etc/volcano. So the headless service informations will be available to all of these all of these pods which are running, and these pods can utilize that resource, utilize that information to basically communicate to each other seamlessly. So this is the scenario of MPI, and right now we have started working with most of the communities because we belong to like Kubernetes domain, and we don't know about TensorFlows or Spark or anything. So we try to communicate with those communities, and we collaborate with them, and we co-work together to make these integrations. So right now, Volcano has a complete support for MPI, for Harvard, for TF operator, for Arena, Spark operator, Chromewell, and Paddle. So there are another like 5 to 10 integrations which are already going on, and which we have planned by the end of this year, we will finish it off. So you can see that there are APIs, and there are two set of APIs, either it's a Volcano job or a pod group. So these frameworks, right, which can be transformed to Volcano job, okay, we try to integrate using the Volcano job, Volcano specs. If these frameworks are not able to integrate with the Volcano specs, then what we do, we create a pod group where we say that, okay, in the pod group, you can define how many tasks should be coming up to finish the whole job. So something like Spark operator, which was quite complicated to transform the complete Spark spec to a Volcano. So we created like a pod group where you can, all the features which are given by Volcano, you can define it in the pod group, and then Volcano can take care of those things. And right now, like a lot of companies have already started working with us, and they are already evaluating Volcano. So there are a bunch of companies who are already evaluating, and in Huawei Cloud, it is already running in the production. So I just have probably a demo video, I will just show it. So in this demo, what I did is I created a Kubernetes cluster in GCP, okay, and I spawned a Jenkins machine in this cluster. And we tried integrating this Jenkins with the Kubernetes cluster, and we have installed Volcano in this Kubernetes cluster. So whenever you have an MPI job or a TensorFlow job, Jenkins can interact with the Kubernetes cluster and deploy your workloads seamlessly. So here is a demo. Like, it's a simple, like you can go to the GCP and create a Kubernetes cluster, a managed instances. You can select the number of nodes and type of node you want. And to connect, basically to connect this cluster, you can copy this command and go back to your local machine and authenticate your local machine to talk to the Kubernetes cluster. And you can just check by running a simple command of kubectl to see whether your local machines are able to interact with Kubernetes cluster or not. After that, what you go, you go to Volcano GitHub project, and there is a quick start guide. So you can just copy one command, okay. So basically this is a YAML which contains all the CRDs and all the information. So you just need to copy this command and run it in your Kubernetes cluster. This will bring up the whole Volcano. All the required components will be spawned. So it creates all the required CRDs, service accounts, configurations, rollback, RBAC. Everything is already integrated in the single YAML, and you can just run one command to install the whole thing. So once the installation is done, you can go to the GCP workloads, and you can see the Volcano components have already started running. So this provides like a seamless support to all of the Kubernetes providers. So you can run the same steps either in EKS or GCP or in Huawei Cloud, wherever like there is a Kubernetes native support, you can use the same command to install the Volcano. And then you can go to GCP and click on the marketplace and basically install Jenkins. So with a click, you can just install it. Basically, it will spawn up a Jenkins VM. And then it will give you, it will expose this Jenkins VM to a particular IP, so you can use the IP and the temporary password to log in. So once you have that, you copy again the Kubernetes service account informations, authentication information, and go to the Jenkins VM, so that you have to make this Jenkins work with our Kubernetes cluster. So you just log in with the Jenkins user and run the same command. So it will authenticate this particular instance of Jenkins to work with the Kubernetes cluster which we created. And then you can run just basic commands to test the connection. So yes, now the Jenkins like VM is able to connect to the Kubernetes cluster we created. So now it will be able to basically spawn all the nodes, spawn all the workloads, whatever we will be running. So once this is in place, I've created a project called OSI demo. So we'll be using a simple So we'll be using a simple TensorFlow example. So this is how you write the Volcano jobs. So you give an API version like bash.volcano.sh, and we are right now in V1 Alpha 1. So once you put these versions and this kind, Volcano controllers will pick up these jobs for scheduling. So you just give a kind as a job, and you define like how many set of tasks should come up before the job execution starts, basically. So you give the minimum spec, and you say that okay, the scheduler name should be Volcano. It should not be using the default Kubernetes scheduler. And then you can define the policies, and these policies can be defined on every level, like on the task level as well as the complete job level. So you can define like if any of the pod gets evicted, basically killed or anything, you need to restart the whole job. And then you have a template for your PS where you say, okay, one replica should come up, okay, and you give the commands whatever you need to run in that. So basically, this will change as per your application, but this thing will remain constant. Basically, I told you whenever these services needs to interact, these tasks needs to interact with each other, they create a headless service. So the information of those services are basically put into /etc/volcano, and then then each of these tasks can pick up those informations and tries to connect to each other. And you can give your Docker image name and all. And then you have a second template, which is basically your worker. And then now you are defining another lifecycle policy in your task, where you say that, okay, the workers, right? If any of these workers all the workers completes basically the job, you say the job has been completed. So like if the PS completes its job, right, still the job is not completed. The worker has to complete the whole job, then only you can say the complete job has been completed. So here also same set of configurations basically. So this is the job we will be trying to run in our demo. And I have written a simple basic scripts to just poll the status of these individual pods and individual tasks, which I will be using in Jenkins. And I have written a Jenkins file where I have mentioned all my steps, okay, scheduling, deploy, scheduling, running. And basically in each of these steps, I will be calling my scripts to just check the status of those pods and those workers. So once this is in place, if I create a pipeline in Jenkins, it will be able to use these steps and use these configurations to basically deploy our workloads. So we go to Jenkins, and in Jenkins I have installed the Blue Ocean pipeline plugin. So you can go to the pipeline, create a new pipeline using the GitHub or any of your SVN controllers. And you can specify your GitHub ID and all. So it will pick up the projects from there, and it will create the pipeline. So this pipeline will basically use our own Jenkins file, whatever we have created in the repository. And once you create, it starts triggering. So basically all the steps, whatever we defined in the Jenkins files will be executed, and all the scripts, whatever we are trying to run, will be executed sequentially. So scheduling happens, all of the scheduling happens in one go. Okay, it's not like the benchmark PS completes, schedules first or then the worker, but the whole bunch gets scheduled in one go. And when it starts running, then you can use a single, we have a command line tool called VCCTL, which can be used to poll the status of the complete job. This was basically my demo. And this is how, like, simply you can use Volcano to run your workloads. Okay. So this, the same experience, if you are trying to run it in Amazon EKS or Huawei Cloud, you will get exactly the same experience. You don't need to change any of these steps to run Volcano or install or basically deploy your workloads. Coming to the summary, like, we have a strong developer community. By strong, we don't say like 1,000 developers or 100 developers. We are a small group of people, but we are interacting with most of the communities for different domains, and we are trying to interact with them and co-work together to integrate all of these domains into Volcano. And we have a one-stop solution for all the AI, ML, and big data workloads. So we have most of the AI, ML, and big data workloads, whatever is there, we are trying to interact with them and trying to bring everything into one hood. So going forward, if you want to run any of these workloads and your application consists of different type of domains, like you have some applications which need some machine learning as well as artificial intelligence, you can basically deploy all of your workload in the same hood using the same command line tool. And it runs seamlessly on all of the Kubernetes service certified providers. It has a one-click installation, and going forward, whenever we will be giving an update, we'll give an update in using the YAMLs, and you don't need to actually do anything. You just need to apply the same YAMLs to all your cluster, and it will take effect. And we have a single command line tool to manage all type of jobs. So you don't need a separate command line tool to manage your ML jobs or separate command line tool to manage your MPI jobs. The same tool can actually manage everything. And we have an efficient scheduling. Okay, so the whole thing is like, in Volcano, the main thing is scheduling. We try to run everything efficiently in a same set of resources. Computing is is getting cheaper, okay, but it is still not that cheap that you can just misutilize your resources. So we try to run everything efficiently, and we try to utilize the resource what you have, right? The set of nodes or the set of clusters. We try to utilize them efficiently, and by doing the backfills or reservations, okay, like that. So that is it. We have a lot of features in place. If any of you wants to contribute to this project, it's like most welcome.